Chapter 2 is all about linear functions, these sort of basic building blocks of functions. And we're going to continue talking about linear functions in section 2.2. And the important idea here is we're going to be modeling with linear functions. And what that means is we're going to be creating our own linear functions. They're going to describe a situation, give us some data, and it's up to us to actually create the linear function. So here we're going to get lots of practice creating linear functions. And before we start creating some, I want to sort of review the important elements of a linear function, as well as some important wording when we're coming across functions described in words. So importantly, we need to remember that when we see or talk about a linear function, this is a function with a constant rate of change. So wherever you take the average rate of change of this function, you're going to get the same exact number. It might be 2, 2, 2, 2, or it might be 1.3, 1.3, 1.3. Anywhere you try to take a rate of change, an average rate of change in the function, you're going to get the same number over and over again. So let's think about what this looks like graphically. And I want to look at two contrasting examples, one that's going to be linear and one that is going to be not linear. So let's first think about a linear function. It might look something like this. And importantly, anywhere you go on this linear function, if you go over 1 unit, so you're going to go over 1 unit, and maybe that forces you to go up 1.7 units. Well, it would be the exact same anywhere on the graph that you did that. When you go over 1 unit, you would have to go up 1.7 to get another point on the graph. Up over 1 unit, up 1.7. And so that is that constant rate of change. But here's an example of a function that's not linear. It's obvious to us that it's not linear because it's not a straight line. But let's think about what that means in terms of the rate of change. So think about maybe right here, you go over 1 unit and up over 1, and you end up going just up like 0.2 units on that part of the graph. But go to another part of the graph and go over 1 unit, and to get back on the graph, so over 1 unit, to get back up on the graph, you might have to go like 2.1 units up. And so in this area up here, things are growing much more quickly than they are over here. Over on the linear function, things always grow, totally predictable. They always grow at this constant rate. But a function that's not linear will have varying rates of change. Luckily for us in Chapter 2, we just deal with linear functions, so everything is very predictable, and this kind of gets our feet wet in dealing with functions, and we'll get some good practice. Before we dive into examples, I want to review some important phrases that tip us off as to what our input and output for a function will be. We've talked about this before, but whenever you see this phrase as a function of, what comes before that phrase and what comes after that phrase are important quantities. What comes before the phrase is your output for the function. And what comes after that phrase will be always your input for the function. This is definitely a phrase that you want to look out for. So like, for example, maybe cost as a function of pounds of material. So, and in a table, we always put our inputs to the left and our outputs to the right. Creating tables is going to be an important skill that we're going to practice a lot today. But this phrase here, look out for. Other phrases you might see, we want to look out for the word models. What comes after the word models is going to be your output. Like it might give you some formula, this formula models, blah, blah, blah. And what comes after is your output. Remember, functions are like these assigners, and if something is modeling something or something is assigning an input, then the thing that it's modeling is your output. So we want to look out for the word models. And as a function of, these are key phrases as we're translating words into formulas. We need to be on the lookout for these. Okay, our first task today, even before we create these linear models, is we need to be able to determine if a function is linear or not linear just by looking at a table of function values. So just looking at values of a function, we should be able to eyeball whether something is linear or not, thinking about the average rates of change. So let's look at a few examples like this. So our first example, I'm going to give you a table in a minute, and we're going to determine if the following tables represent linear functions. And the only way we know how to recognize a linear function is hopefully, if it is linear, it'll have some constant rate of change as we're looking at the data. Okay, here's our table. The number of branches of an oak tree and a birch tree since 1950 are represented by the following tables. This example actually comes from Khan Academy. So here we have the oak tree data, and down here is the birch tree data. And it looks like years since 1950. So this would have been in 1950. There were 34 branches. In 1953, there were 46 branches. In 1956, there were 58 branches. In 1959, there's 70 branches, and 1962, there's 82 branches. Okay, and so let's start with the oak tree, and let's try to determine if this is a linear function. So importantly, these are all evenly spaced inputs, and we'll see why that's important. So what's going on here? Well, between these 3 years, we gained, let's see, 34 to 46. That would be, whoops. So 34 to 46 is going to get us 12 more branches. So we gained 12 branches between those years, those 3 years. This is 58. And between the next 3 years, let's see, how many did we gain? 46 to 58, another 12 branches. From 1956 to 59, looks like we gained another 12 branches. And then from 1959 to 1962, 70 to 82 branches, another 12 branches. Okay, so this is definitely sizing up to be a linear function because every 3 years, the tree grows 12 branches. It doesn't matter which 3-year period we're looking at, it's growing at that same rate. So we could say every 3 years the number of branches increases at a constant rate. That's important. Of, let's see, we found it was 12 branches every 3 years. And we can think of that as, on average, 4 branches per year. So this is definitely linear. It's growing at a constant rate. Okay, let's take a look at the birch tree. So the birch tree, again, our time is evenly spaced, but this time it's every 10 years what's happening. So let's see, from 1950 to 1960, we went 8 to 33. Every 10 years, it's definitely growing. And I'm getting a little bit suspicious that it might not be linear because to me it looks like it's growing slowly and then quickly later on. So in the first 10 years, it went from 8 to 33 branches, so that's 25 branches in those first 10 years. And then from 1960 to 1970, it looks like, let's see, 128 minus 33, it grew another 95 branches. Definitely not the same number, or even close. From 1980 or 1970 to 1980, it's going to grow 384 new branches. And then from 1980 to 1990, it actually grows 1,537 branches. So my suspicions were right. This birch tree, the number of branches as a function of time is definitely not a linear function because it's growing at different rates depending on what time period you're looking at. So for the birch tree, every 10 years, the number of branches is increasing at an increasing rate. So we can say that this is not linear. It may be something else that we learn about later in the course, but it's definitely not linear because the key was that the rate was not constant. We had an increasing rate of change. Okay, for example 2, same story. Determine if the following table represents a linear function. And for this example, we're going to go pretty basic. We're just going to say our input is x and our output we'll call y, which is also f of x, a function of x. And here's our data for this function. And upon first glance, I look at these outputs. They seem to be growing at fairly very regular intervals. But hiding in the first column is the fact that my inputs are not evenly spaced. So in fact, this will end up being not linear because from 1 to 2, we increase 5 units. But then going from an input of 2 to 4, it took us that long to get an increase of 5 units in our output. And it took us even longer to get an increase in our output of 5 units. Going from 4 to 10, it keeps taking longer. So if we were finding the average rates of change between, say, these two numbers, or these two data points and these two data points, we would find very different numbers. Another way to think of it is if I graphed this data. Let's take a look at that. So as I graph this, I'm going to have my inputs on the horizontal, my outputs on the vertical, and this is sort of my range of output values. And I'll go ahead and put my the domain of it. Okay, so let's see if I had 1, 2, 4, 10, and about 23. These are my input values, and I know that 1 has an output of 5, 2 has an output of 10, 4 has an output of 15. Things are already starting to slow down. You can kind of start seeing this curve in the data. And then 10 has an output of 20, and 23 has an output of 25. So this data, even though the outputs look like maybe they were going to yield a constant rate of change, because the inputs were not evenly spaced, we see that this is definitely not linear. So watch out for this. A table of data, you have to be able to say unequivocally that the average rates of change never change. And that will depend on if these are all evenly spaced. These definitely need to be evenly spaced, and they're not in this case. You could always, just double check yourself by saying, I'm actually going to find the average rates of change between those two numbers and these two numbers and verify that they're actually different numbers, and you'll find that they are. Okay, now we're ready to dive into modeling linear functions. So actually creating some formulas based on data that they give us. And in example 3, we're going to look at average sleeping times depending on what your age is. So we have this wonderful sleeping baby who is literally smiling as he or she is sleeping. And here's the information that they give us. A 2-year-old child sleeps 12 hours per day on average. It has been estimated that as the child grows up, the amount of daily sleep will decrease every year by 15 minutes until the age of 18, when it will level off. Construct a linear function that describes sleep as a function of age between the ages of 2 and 18. Sketch this function. Okay, we are going to pick this apart and we're going to come up with an answer to what they ask us to do. Let's outline our basic strategy here for constructing this linear function. So when we're going to construct a linear function, the first step in our strategy, our process, is we're going to find out what the input variable is and what the output variable is. Find what is the input and output variable, each of those. And that's really a big step. That's a very clarifying step. Once you're really confident on what the input and output variable is, it makes it so much easier to translate all these words in here and tease out the data. And so that's the very next step, is we want to collect any data that they give us in the table. So collect data in a table, and those two are really the hardest steps. Once you have good data in a table and the fact that we know it's a linear function, we'll just use one of the forms of a line to create the equation for this data. And I always like using y equals mx plus b. I think it's the simplest. So then construct your linear function. So let's use these 3 steps on this example. The first step says we need to find what is the input and the output variable. And I'm just going to tell you, it often comes at, well, it can't come at the beginning, but this one happens to come at the end, and they often come at the end telling you what the input and output variable is. Okay, construct a linear function that describes sleep as a function of. Okay, that phrase right there, that's an important one that we talked about earlier, and we've talked about it in different sections. As a function of. The thing that comes before is your output. So sleep as a function of age. And the thing that comes after is your input. So if we're going to construct a table, then here we have described what the input and the outputs are. And so I know sleep is my output. Should I just put sleep here? No, I really need to describe what do they mean by sleep. It's the number of hours that a person sleeps, right? So the number of hours of sleep, and we'll call that H, the number of hours of sleep. And then the input they say is age, and so we have to decide, are we going to, what are the units of this age going to be? And the most logical one is to say the age in years. Okay, we have done step 1. We've found what the input and output variable is. Our next thing to do is collect data in the table. I reread the very first sentence. A 2-year-old child sleeps 12 hours per day on average, and that's my first data point. A 2-year-old child sleeps 12 hours. Next, it's been estimated that as the child grows, the amount of daily sleep will decrease every year by 15 minutes. Okay, they don't out and out give me another data point, but they give me enough information that I could construct my next data point. If at 2 years of age, they're sleeping 12 hours, this right here tells me that at 3 years of age, they're going to be sleeping 11 hours and 45 minutes. So at 3 years of age, okay, what should I put here? 11 hours, 45 minutes. I really need to use a decimal number because my formula is going to be dependent on real numbers, not clock time. So the decimal number for 11 hours and 45 minutes is, that's 11 hours and 3/4, or 0.75 hundredths of an hour. I've done the 2 hardest parts. I've found the input and outputs. I collected some data. When you have a linear function, you only need 2 data points. And from here, we can use y equals mx plus b to construct the actual formula for the function. Okay, I know that I want to use this form of an equation of a line, and so the very first thing that I want to do is I'm going to go find what the slope is. And the slope will be the difference of the y values over the difference of the x values. And that will be 12 minus 11.75 over 2 minus 3. And most common error I ever see when people are trying to find slope is they get things mixed up. They might have this in the right order and then these in opposite order. So just be careful as you're finding slope. This will be 0.25. And is this over 1 or negative 1? It should be negative 1. So our slope is negative 0.25. This is slope. Okay, now I'll use that slope in this formula. Plus I know an x and a y that I can plug in, and that'll help me find what b is. So I'm just going to use this data point as my x and y. So here's my y. 12 equals the slope times x plus b. I have everything but b, so I can solve for b. 12 will equal negative 0.5 plus b, and I can add 0.5 to both sides. And I find out that b is equal to 12.5. Have everything I need to put it all together. I've found that y equals negative 0.25, the slope, times x plus b, which is 12.5. But I'm actually going to put it in the context of the problem using the variables that I already outlined. So the hours that a person sleeps as a function of age is negative 0.25 times their age, times that input, plus 11.5. And this is it. This is what we were asked to do. We constructed a linear function that describes sleep, the number of hours of sleep, as a function of age. So you give me any age between 2 and 18, and I can tell you what this model predicts that person should sleep. Here's our last example for this section. The Corona Company has determined that the total cost of manufacturing 20 televisions is this much, and the total cost for 25 televisions is this much. Assume that the relationship between cost and volume produced is linear. We will explore cost as a function of volume produced. Okay, we got all this stuff about producing televisions and the cost of doing that, and now we get our first task to perform. Construct a table of this data with the first column the independent variable and the second column the dependent variable. Great, that's what we needed to do anyway, so that's good that that's the first thing they asked us. Okay, back in the information as a function of, this is that important phrase that we want to look for, and cost comes before that phrase, volume produced. So cost is definitely our output or input. It should be our output. Output comes as a function of our input, volume produced. Okay, here's the start of our table. Cost is our output. We decided volume produced is our input. And we just go back and tick through and see if we can get some of the data out. And it looks like for sure we can. They tell us that when 20 televisions are produced, that the cost to do that is $3,951.20, and when 25 televisions are produced, the cost to do that is $4,514 even. Awesome. So we have our data in the table. Then that wasn't too rough. It was the data was kind of sitting right in the problem. Next, we're asked to determine the linear equation that relates cost as a function of volume produced. And we'll just use these two data points. Because we know it's a linear function, we just need the two data points. We'll let this be the model that we're going to use, y equals mx plus b, and to find the slope. Same old story, we'll take the difference of the y's over the difference of the x's. And this will be 562.80 divided by 5, which simplifies to our slope being 112.56. So we'll use that slope and we'll pick one of the data points. I'll pick this one, and we'll put it into the formula for y equals mx plus b, and we'll solve for b. So 4514 will equal the slope, 112.56, times that input value 25 plus b. And solving that, we'll find out that b equals 1700. So y equals 112.56x plus 1700. And I want to write it in the using the variables of the problem. So the cost as a function of volume produced will be 112.56 V for every unit produced plus 1700. And this is what they asked me to do here. Okay, next, use the function to determine the cost of manufacturing 28 televisions. We're actually going to leave this part of the problem for you to do as part of the quiz, but you know that you're going to use the function we just found, and we're going to determine the cost, so determine C when we're making 28 televisions. Continuing the same problem, the next thing we're going to do is sketch this function, label the horizontal and vertical axes, and the horizontal axis needs to be our input, and the vertical axis needs to be the output. And input for this example is V, that volume produced, and output is that cost, or C, and that'll be in dollars. So here's the function that I want to graph, and I know it's a straight line. I could use the data in the table. I can also just kind of think through, what if V equaled 0? This whole term would be 0, so C would equal 1700. So if C equals 0, no, if V equals 0, then my cost is 1700. And then I am going to use one of the data points from the table. There was a data point 20, 39, 51, 20. That's a point on the line. So I can graph that point 20, looks like 39, 51, 20, and then it is a straight line, so I just need to essentially connect these two lines, and this is the graph of my function. This is how cost is growing as the number of televisions is produced. Last thing we're going to look at here is, what are the practical interpretations of the vertical intercept and the slope of the graph of this function? So practically speaking, the vertical intercept, which is right here, means that when 0 televisions are produced, the cost to do that is 1700. And you think, why would it cost anything to produce 0 televisions? Well, you have to, before you produce even the first television, you have to maybe pay some real estate location, pay some payroll costs. So there are costs associated even before you begin producing your first television. So we say the vertical intercept is at 0, 1700, and the meaning, what we just talked about, when 0 televisions are being produced, the cost is 1700. Okay, so now we want to think through, what is the meaning of the slope of the graph? The slope of the graph is 112.56, and what does that mean in the context of this problem? For every 1 unit I go over, I go up 112. 1 over, up 112. So the slope is 112.56, and the meaning is that for every additional television produced, the cost goes up 112.56. So let's think through the big ideas from this section. There were really 2 major ideas. The first was being able to tell from a table whether a function is linear or not. And the other one, even more major, in the last 2 examples, we saw how to create the formulas for linear functions, and that's what modeling linear functions means. This was a big deal, and we'll get some more practice doing this in the homework.